Hi everyone, welcome back to Dave's Math channel. This is my 8th video on my series on algebraic number theory, and this will be my first in a sub-series on Gaussian primes. This picture in the middle, I think you're probably familiar with this by now. This is a picture of the Gaussian primes up to some norm limit. I think the norm here is about, I don't know, the absolute value is about 20, I think. Anyway, let's begin. So, what we're getting at here, the reason we're interested in all this, remember the pullback thing I was telling you about last time? I want to prove a theorem. So what we really want to get here is ultimately we want to get, and this is for several videos from now, what we want to get is a formula for the number of ways you can represent an arbitrary positive integer as a sum of two squares. And remember that not every positive integer can be represented as a sum of two squares. For instance, I think 6 is the smallest counterexample. You can't write 6 as a sum of two squares. Can't write 7 either. But some numbers you can write as the sum of two squares, like squares. I mean, I'm saying two or more squares, I guess. So, or at most two squares. So obviously squares you can write as one square, like 1, 4, 9, 16. But then there's other numbers you can write as a sum of two squares of two positive integers, like 5 is 2 squared plus 1 squared, 10 is 3 squared plus 1 squared, 13 is 3 squared plus 2 squared, and so on. And there's a nice geometric way you can picture these points. They're just points on a circle centered at the origin. So you can, if n is a positive integer, then you can look at the circle centered at the origin with a radius of square root of n, and you can ask how many integer points, how many points with x and y, both integers, lie in that circle. And the picture I show on the bottom of the slide corresponds to n equals 25. This is just a circle of radius 5. 5 is the square root of 25. And I think you guys probably know there's exactly 12 points, 12 integer points on this unit circle, namely plus or minus 5 comma 0, plus or minus 0 comma, 0 comma plus or minus 5, plus or minus 3 comma plus or minus 4, and plus or minus 4 comma plus or minus 3, just because 3, 4, 5 is a right triangle. So anyway, so there's 12 points on this circle, and so there's 12 solutions. If you include positive and negative, then you don't care about order. Anyway, so that's ultimately what we want to get out of all this. But I'm going to prove a theorem that's sort of in the direction of this result. It's not going to be the full result. We're going to need to do a lot more work first. But what we're going to do, here's the theorem I want to prove today. So we're going to let P be an arbitrary prime that's congruent to 1 modulo 4. In other words, P is a prime of the form 4m plus 1, where m is an integer. So for instance, 5, P equals 5 is the smallest example, such a prime. And then 13, 17, 29, 37, so on. So those are all primes that are congruent to 1 modulo 4. Turns out that every odd prime is either congruent to 1 or congruent to 3 modulo 4. I think that's pretty obvious because every odd integer is as well. But there's only one even prime, that's 2. That's kind of the only odd man out. So anyway, just a little heads up here. If P is a prime congruent to 3 modulo 4, it turns out there are no, it isn't possible to write P as a sum of two squares. But if P is a prime congruent to 1 modulo 4, there's a unique way to do it, where we're saying P equals a squared plus b squared, where a is greater than b and a and b are both positive. It turns out that for every prime congruent to 1 modulo 4, there's a unique pair of integers a comma b satisfying those conditions, such that p equals a squared plus b squared. Pretty nice result. I'm not going to prove it's unique today, but I am going to prove existence. So this is what I want to prove. I just want to prove that there exists two integers, a and b, both positive, with a greater than b. I guess you don't really care about that since we're only proving existence, but let's just, for, to be nice about this, let's say a is greater than b, and p is a squared plus b squared. So that's what we want to prove. But in order to prove this, we need 4 intermediate results. These are called lemmas. So a lot of times when you're proving theorems in math, you first have to prove some intermediate results. Those are called lemmas. And you'll find you do this a lot when you do proofs in math. You find you have to prove a lot of lemmas first. But sometimes the lemmas turn out to be really important in and of themselves. As a matter of fact, there's some very famous mathematical lemmas, like Zorn's lemma and Minkowski's lemma. I'm not going to go into this too much, but sometimes people are trying to prove a big result and they end up proving some important lemmas on the way. I don't think any of the lemmas I'm going to prove today are really all that important. They're just kind of, stepping stones on the way to proving this theorem, which is a pretty important result. But anyway, let's just start. So let's look at the first lemma. I'm calling this lemma 1.1. The theorem I'm trying to prove is I call that theorem 1, and then I'm giving the lemmas 1.x, or x increases. So let's look at lemma 1.1. And some of these lemmas are going to look a little strange to you guys, I think. So lemma 1.1, this is probably the most difficult one I'm going to do today. This is actually a lemma involving group theory. And group theory isn't really, group theory is part of abstract algebra. So it is worthwhile to know some group theory. I didn't mention this earlier, but you remember algebraic number theory deals with abstract algebra. And group theory is actually, I think, the most basic concept in abstract algebra. So if you don't know any group theory, I have made a few videos on group theory. I suggest you watch those first. Anyway, I don't think basic group theory is all that difficult. So, watch some of my basic videos on basic group theory. They're pretty basic. And this lemma doesn't involve anything complicated in group theory. It just involves cyclic groups, which are the simplest type of groups. So you don't have to know a lot of group theory to understand this lemma. But just a little heads up, you do need to know group theory. So here's the lemma. Again, we're letting P be an arbitrary prime. Just arbitrary, doesn't even have to be congruent to 1 mod 4, it could even be 2. Any prime you want. And now we're going to consider this set, which I call ZP star. And ZP star is is just the set of integers from 1 to P minus 1. 1, 2, 3 up to P minus 1. Not a very complicated set. And of course, there's P minus 1 elements. But now we're going to make it into a group by giving it a binary operation, which I'm calling times. But it's really multiplication modulo P. And this is another thing you have to know about, modular arithmetic. And again, this isn't a very complicated topic. It's just remainders. Modular arithmetic just deals with remainders. So when I say mod p, really I'm saying the remainder after you divide by p. I hope that's not too complicated, but just keep this in mind. So we have this set of numbers from 1 to p minus 1. They're all less than p. And now we're also including with that set multiplication modulo p. That means, for instance, if p was 5, 2 times 3 would be 1, because 2 times 3 is 6. That's 1 mod 5. And 3 times 4 would be 2, because 3 times 4 is 12, which is 2 mod 5. I think you get the idea. So that's multiplication modulo p, and you could do it for any other prime p. And so this gives us and then I just want to prove that this set with this binary operation I've just defined is a cyclic group. It's not just a group, but it's a cyclic group. It's a cyclic group of order p minus 1. So how do we prove this? Well, first we have to prove it's a group. That's kind of the easy part. So how do we prove it's a group? Well, you have to know what the axioms of group theory are. There's 3 or 4, depending on how you count them. There's, if you include closure, there's 4 axioms of group theory. The first one is closure. That just says that the group multiplication this time, in this case, multiplication modulo p is closed. This set, which I'm called ZP star, is closed with respect to multiplication modulo p. Well, that's pretty easy to see. All that means is that for any 2 elements of this set, you can multiply them, take the remainder modulo p, and that should be another element of this set, which it clearly is. So it is closed with respect to multiplication. That's the first axiom. Second axiom is associativity. And that follows right away from associativity of multiplication. We all know that ordinary multiplication is associative. And it's still associative if you reduce modulo p or modulo any modulus. That doesn't affect the order of the operations. So I think that's pretty clear that it's also associative. And so those are the first two axioms. Then you have to show that it has an identity element. Well, that's pretty easy to see too, because 1, the element 1 is clearly an identity element. 1 is the identity element of ordinary multiplication. And when you take it modulo p, you're always going to get back 1, because 1 is less than p for any prime p. So that's pretty easy to see that 1 is the identity element. Well, now there's just one more axiom we have to check, inverse. So we have to show that every element of this set has a unique inverse modulo p. And this one you have to be a little more clever. But you can use the extended Euclidean algorithm to prove this. Remember I was talking about the Euclidean algorithm yesterday in my last lecture? So Euclidean algorithm clearly works for integers, ordinary integers. I mean, that's kind of how it was developed. That's how Euclid came up with the algorithm. He didn't know about any of these other fancy, rings. Those came much later. So we only care about the integers here. In this case, integers modulo p. And so what we do, here's what we do. We're thinking of these ordinary integers now. We want to show, let's say a, let's just let a be any element of our set that we're starting with, zp star. That means a is just any integer between 1 and p minus 1 inclusive. And we want to show that there's a unique inverse of a. We'll call it b. So we want to show that there existed an integer b such that ab, the product ab, the ordinary product ab, is congruent to 1 modulo p. That means that a cross b is equal to 1 in this group because we're doing everything mod p. So how do we prove that? Well, it's actually pretty easy. We use the extended Euclidean algorithm. So first we consider the GCD of A and P. And since P is a prime, that means that every number that's not a multiple of P, which includes A, is relatively prime to P. That's pretty easy to see. That's always the case. For any prime P, any number that's not divisible by P is necessarily relatively prime to P. Leaves you a GCD of 1. So if you apply the extended Euclidean algorithm, first of all, you know the GCD is 1, but if you apply the extended Euclidean algorithm, you don't even have to do this really, but you know that there exists an element B, because you know that since 1 is the GCD, you can write A as B times 1 plus C times, or no, 1 is B times A plus C times P, where B and C are some integers. There exist integers, such as this case. Well, that means, we can ignore C times P because we're doing everything modulo P. That just means that 1 equals A times B, or B times A. It doesn't matter because multiplication is commutative modulo P. So that means that B is a multiplicative inverse of A modulo P. That's nice. And this is a very nice result, by the way. It turns out that for any prime P and any integer A that's not divisible by P, this integer always has a multiplicative inverse modulo P. We kind of proved that. So that completes our proof that this thing is a group. This set I'm calling ZP star together with multiplication modulo P is a group. But we're still not quite done. We still have to prove it's a cyclic group. So we still have a little bit of work to do. Well, the next thing you'll notice, it's not just any old group. It's an abelian group, which is just another way of saying a group in which the group multiplication is commutative as well as associative. And that's pretty easy to see because our group multiplication is this ordinary multiplication modulo P, and we all know that ordinary multiplication is also commutative, so it's still commutative modulo P. So again, that just proves that this group is an abelian group. But now you have to know something about abelian groups. Well, there's actually two cases to consider here. There's the case where P is 2. That's kind of a trivial case. If P is 2, then this set only has one element, just 1. So this is a pretty boring set. It's still a group because you just have one element, 1, and you're giving a multiplication. But that's not very exciting because 1 times 1 is 1. You really can't do anything. This is known as the trivial group. It turns out there's only one group up to isomorphism of order 1. It's called the trivial group. It's the most uninteresting group in the world, but it is a group. And it's a cyclic group as well. So the case p equals 2 is a trivial case, and it's trivially true for p equals 2. So then we can just assume that p is odd, because 2 is the only prime that's even. So if p is an odd prime, what do we do? Well, if p is prime, if p is odd, then p minus 1 is even. So now we know that we have a abelian group of even order. And now you have to know a little bit about abelian groups. I'm not going to prove this, but it turns out that every abelian group of even, or the only abelian group of even order up to isomorphism that has just one element of order 2 is cyclic. That's true. I'm not going to prove that, but it is true. If you think about it, I think it'll make sense to you. Abelian groups that aren't cyclic, you can write them as a direct product of cyclic groups. And if your group has even order, it turns out that you're going to get more than one element of order 2. You'll have to trust me on that, but it's true. So anyway, so since and then the last thing you just have to note is that this group, this particular group we're defining here, does have a unique element of order 2, namely minus 1 modulo p, or p minus 1. P minus 1 is connected to minus 1 modulo p, and we all know that negative 1 squared is 1. So it's pretty easy to see that p minus 1 is a unique element of this group that has order 2, because there's no other number you square to get 1 modulo p. Anyway, that completes the proof. So that was a little tricky, because we had to know some group theory, and we had to prove some properties of this set, prove that it's a cyclic group. But we're done with that. So that was probably the hardest thing we're going to do today, actually. Now I want to prove 3 more lemmas. So these are easier, like I said. Lemma 1.2, now we're going to let p be a prime of the form 4n plus 1. So now we're going to let p be a prime congruent to 1 modulo 4, like 5, 13, 17, so on, but not 2, 3, or 7, or 11, or any of those other ones. So anyway, now we're going to prove that if that's a case, then there exists an integer k that's a positive integer k less than p over 2, such that k squared is congruent to, I think this should be minus 1. Did I write 1? I think it should be minus 1 modulo p. I might have made a typo here. Yeah. So so how do we prove that? Well, we already showed in the previous lemma that ZP, the set ZP star along with multiplication modulo p is a cyclic group of order p minus 1. Well, in this case, since p is 4m plus 1, this is a cyclic group of order 4m. So now, every cyclic group has a single generator, and in the case of ZP star, this generator is called a primitive root modulo p. So what that says, for every prime p, there's a thing called a primitive root modulo p. That's just a number a, such that the set a, comma a squared, a cubed, a fourth, all the way up to a to the p minus first power. That's just reordering of the set 1 up to p minus 1. Kind of a neat result. It's a what's called a permutation of that set. Kind of a neat result, I think. There's a lot of neat stuff in group theory, but anyway, it's well known that every cyclic group has a single generator, so we just called A as the generator of ZP star. And so we know that there exists such a number A between 1 and p minus 1. And it's not 1. It can't be 1 because 1 has order 1. This thing has to have order p minus 1 or 4m. And now we consider a to the mth power. And I'm claiming that this number k we're looking for is it's either a to the m or a to the 3m. But the property, if we call it k1, let's say k1 is a to the mth power. Well then, notice that k1 squared, that's going to be a to the 2m, and that's going to be minus 1 because a to the 4m is 1. And remember what I said earlier? This is a cyclic group of order 4m, so we know that a to the 2m quantity squared has to equal 1, and the only numbers whose square are 1 modulo p are plus or minus 1, and it can't be plus 1 because we already said that this group has order 4m, not 2m. So that means that a to the 2m has to be congruent to minus 1 modulo p, and that's k squared. So yeah, k squared is congruent to minus 1 modulo p. That's what we wanted to show. This number k1 has that property. We're not quite done because we also needed that k1 was less than p over 2. Well, there's two cases. There's two possibilities. Either it is less or it's greater. You know, let's suppose that if it's less, we're done. Now we don't have to do anything else. But let's suppose it's greater than p over 2. Well, it still has to be less than p because the biggest it can be is p minus 1. But now consider p minus k1. And let's look at p minus k1 quantity squared. Well, modulo p, that's just negative k1 quantity squared, which is the same as k1 quantity squared, which we already showed was congruent to minus 1 modulo p. So we're done. And p minus k1 has to be less than p over 2 if k1 is greater than p over 2. So we're done. In the first case, we can let k be k1. In the second case, we can let k be p minus k1. So we just proved what we wanted. Anyway, so that's lemma 1.2. And lemma 1.3, this is kind of a different type of problem here. This concerns Gaussian integers. Now we're going to get back to Gaussian integers again. And this is another pretty easy lemma. So what this lemma says, well, we're letting alpha and beta be arbitrary non-zero Gaussian integers now. And now we consider the GCD. Remember yesterday I was talking about how we showed that the Gaussian integers, Z of I, the ring of Gaussian integers, is a Euclidean domain. That means that we can compute the GCD of any two Gaussian integers. And I even showed how you can do that using the Euclidean algorithm. So we know we can do that. That means that this thing gamma, this thing I'm calling gamma, which is the GCD of alpha and beta, this is another Gaussian integer. It's a well-defined Gaussian integer that we can actually compute. And now what I'm claiming with this lemma is that if this is the case, then the norm of gamma has to divide both the norm of alpha and the norm of beta. This is a very useful result, turns out. And it's actually very easy to prove. I mean, we know that since gamma is the GCD of alpha and beta, GCD stands for greatest common divisor. And since it's a common divisor, it has to divide both alpha and beta. So we know right off the bat that gamma has to divide both alpha and beta. That means there exists Gaussian integers, which I'm calling mu and nu here, such that alpha equals mu times gamma, or gamma times mu, and beta equals gamma times nu. And now we can compute the norm of alpha and beta. So the norm of alpha is just the norm of gamma times mu, and we know norm is multiplicative. I showed that yesterday too. That means that this is equal to the norm of gamma times the norm of mu. And similarly, the norm of beta, that's the norm of gamma times nu, that's equal to the norm of gamma times the norm of nu. So you see that they're both divisible by the norm of gamma. So we're done. That was a pretty easy lemma to prove. Now we just got one more. Now we just got one more lemma. So the last lemma, this one I think is a little bit trickier. I'm going to actually construct a Gaussian integer of norm p. Again, we're letting p be a prime of the form 4m plus 1, a prime congruent to 1 modulo 4. And we're going to let k be the number we found previously, the unique integer less than p over 2, such that k squared is congruent to minus 1 modulo p. And now we're going to construct another Gaussian integer, k plus I. So that's just a Gaussian integer with imaginary component 1, or I, if you like, and real component k. So it's kind of mainly along the x-axis. It's just one unit up in the y-axis, kind of close to the x-axis if k is large. And P is also a Gaussian prime. Remember that every ordinary integer, a Gaussian integer. These are both Gaussian integers. And Gaussian integers is a number of the form a plus bi, where a and b are arbitrary integers, so nothing says we can't let b equal 0. That means that ordinary integers are also Gaussian integers, in particular p. That's just a prime here. That's an ordinary integer, so it's also a Gaussian integer. So we can apply the Euclidean algorithm to compute the GCD of p and k plus I, because those are both Gaussian integers. And now I'm claiming that GCD, which I'm calling pi here, and I think, the reason I'm calling it pi, I don't explain it here, but the reason I'm calling this Gaussian integer pi is because it turns out it's going to be a Gaussian prime. I'm not going to prove that today. But we're going to get a Gaussian integer called pi whose norm is equal to p. And that's a very useful result. And we'll be almost done once we see this. This is pretty easy to prove too. So how do we prove this? Well, it's pretty easy. We know that, but we can just apply the Euclidean algorithm to compute pi. And we know that, we could just use the previous lemma actually, because we know that we just compute the norm of p and the norm of this other Gaussian integer, which I guess I don't give it a name, I just call it k plus I. But the norm of p is p squared. That's pretty easy to see, because it's p times its conjugate. The conjugate of p is p, since p is real. So it's just p squared. And the norm of k plus I, that's going to be k squared plus 1. But remember we said k squared was congruent to 1 modulo p. That means there exists some integer a such that k squared is equal to ap minus 1. Well, that means that the norm of k plus I, that's k squared plus 1, that's equal to a times p. So now we have two Gaussian integers that we're computing the GCD of. The first one, p squared, has norm p. The second one, k plus I, has norm a times p. Or the first one has norm p squared. Second one has norm a times p. And it's pretty easy to see that the greatest common divisor of p squared and ap is equal to just 1, because it's p times the GCD of p and a. But since a is not divisible by p, the GCD of p and a is 1. So the GCD of these norms is equal to p. And we know that from the previous lemma, lemma 1.3, that the norm of pi has to divide both the norm of p and the norm of k plus I. And that means that it has to be equal to p, because p is the only positive integer that divides both of those. It is the GCD. So that proves the lemma, that the norm of pi is p. And it turns out that pi is also a Gaussian prime. But I'm not going to prove that today. And now we're almost done. Actually, I didn't finish proving the theorem. So I finished proving the lemma. That's in the middle of this slide. Now to finish proving the theorem, it's very easy from this point. Let's just consider the norm of pi. So pi, remember, pi is a Gaussian integer of norm p. So we can write pi as a plus bi. This a is a different a than I was using before. But there are integers a and b, such that pi equals a plus bi. And since that's the case, that means the norm of pi, which we just showed was equal to p, has to be a squared plus b squared, because that's by definition the norm of pi. So that completes the proof that p, we can write p. If p is any, this is really nice, because now what I just proved is that for any prime p that's congruent to 1 modulo 4, like 5, 13, 17, so on, there exist integers, and I'm not saying they're positive here, but there exist two integers. Actually, I'm calling them u and v here. We'll get to a and b in a minute. There exist two integers, u and v, such that p equals u squared plus v squared. Well, now we're basically done. We can define a and b very easily. Just let a be the max of the absolute value of u and the absolute value of v. So a is going to be positive, and it's going to be greater than b, which we're going to find to be the minimum of the absolute value of u and the absolute value of v. So now we do get the conditions we want. We get that P equals a squared plus b squared, and a is greater than b is greater than 0. A and b are both positive integers with a greater than b, and a squared plus b squared equals p. So we're done. We just proved what we wanted to prove. So that completes the video for tonight. We just proved a very useful result in number theory. We were able to prove that for every prime congruent to 1 modulo 4, it can be written as a sum of two squares. And it turns out that this representation is also unique. I haven't proven that yet. There's a few other results I still need to prove. This is the main one, but we have to prove uniqueness. We also have to prove that if P is another type of prime, well, it turns out if P is 2, it can also be written as sum of two squares. Pretty trivial, like just 1 squared plus 1 squared. And if P is congruent to 3 modulo 4, like I said earlier, you can't do this. So anyway, that completes my video for tonight. Thank you for watching. Long live math, and I'll see you guys next time.